Okay, so hello everybody. Let's hope I don't faint during the presentation. My name is Kimmo Kärkkäinen. I work as a doctoral researcher at University of Oulu in Finland, and my presentation title was already given by the chairman. So this expands on this novel idea that was recently introduced in this article. This is to estimate the fatigue limit in variable amplitude loading, and I would like to extend a special thanks to my friend and colleague Joona Vaara, who is always asking the right questions for these ideas to be conceived. So first of all, to define over and underload. So overload is this tensile loading spike, and underload is a compressive loading spike in the otherwise constant amplitude based loading, and they tend to occur quite frequently in engineering components and may significantly influence the crack propagation, and they have been studied quite a little from the fatigue limit point of view, and there's nothing really in literature to account for them quantitatively in estimation of the fatigue limit. So usually what we observed in terms of crack propagation rate after an overload, there's this delayed significant deceleration, and after an underload, there's usually this more immediate acceleration effect. And these are mostly explained through crack closure and residual stresses, which basically both stem from crack tip plasticity. So the general categorization is that overloads are good, but underloads are bad. But this may not necessarily apply to near threshold based loading, as was suggested by the results of Pompetsky and colleagues in the 90s. So they showed that both over and underloads were able to facilitate crack propagation below the fatigue limit, so essentially lower the effective fatigue limit. We read about the resistance curve, which is a tool that is going to be used in this analysis. It's just a simple and effective method to depict the development of crack propagation resistance, so which is basically thought to consist of crack closure, and it carries information on the fatigue limit and links to Kitagawa-Takahashi diagram and so on. So first we will use this very simple finite element model to simulate the crack closure response to overloads and underloads. So this is just a two-dimensional plane stress plate with a 0.5 millimeter middle crack, and quite a fine mesh near the crack path to adequately capture the plasticity. And in terms of loading, we have this constant amplitude base loading, which is basically the fully reversed fatigue limits. And then the over and underloads, they are normalized by this yield stress. And you can see the values used here. So absolutely the overload magnitudes are a bit lower because they have a more significant effect. And material model is quite simple, just a steel simple bilinear model with kinematic hardening. This is how the crack will propagate in the model. So it's realized by releasing the current crack tip node. So the crack always jumps one element forward at a time, and this occurs at maximum load every other load cycle, and the final crack length is so that the initial crack size is doubled. And these are the crack closure results, so presented in terms of the opening level as a function of crack extension. So you can see the loading spikes applied at the 0.4 mark, and with overloads we observe this somewhat delayed increase in closure, which is expected, and underloads cause this what is basically just a resetting of the closure development. But what is very important in terms of this study is that both loading spikes can basically remove the pre-existing crack closure momentarily here. That is due to crack tip blunting that not only occurs with overloads but with underloads also. So it is basically with overloads it's caused by the large plastic zone ahead of the crack tip, and with underloads it's actually the reverse plasticity of the pre-existing crack flank that causes this. So here in the crack profiles you can see the loading spike is applied at the 0.4 mark, and you can see a kink in the crack profile in both overload and underload case, and that is like indicative of crack tip blunting and will remove existing closure. So with underloads, if the underload magnitude is high enough, it can be even so that the entire plastic wake is basically completely removed. So this state now corresponds to a new crack without any loading history, and you can see with the closure development that the in this case the post underload closure development corresponds exactly to that of a new crack because the state is effectively equivalent. So what is now the effect on fatigue limit when these loading spikes are recurrently applied? Well, for this we will need the resistance curves, and we know that the closure response should closure development should correspond to the resistance curve, and also the resetting of closure should correspond to the resetting of resistance curve. So with underloads, we saw this basically this just a pure resetting of the closure development. So we will use this default resistance curve for that. But with the overload cases, the closure, the resistance curves are modified a little bit to basically correspond to the predicted closure response. So this is basically the analysis foundation, that the resistance curve would be reset by a loading spike, and the shape can be altered by an overload, but not by an underload. So now the question is that when is a loading spike applied? Well, if we have some load level that is below the constant amplitude fatigue limit, and we assume relatively rare events of these loading spikes, then the most likely place that the loading spike is experienced is in the state where the crack is non-propagating. So basically what happens here is that the crack will extend from the initial crack until it hits the resistance curve. So now this state is the one that the crack will probably spend the majority of its time. So we can assume that the loading spike and underload in this case is applied there. So when the underload is applied, then the resistance curve is reset, and now the crack can continue its propagation until it hits the new resistance curve. And this can go on and on until the loading curve, the delta K curve, no longer intersects with the resistance curve, and then we know that we have surpassed the fatigue limit for that specific number of loading spikes, and the crack is let loose, and the component or anything will fail. So now the question becomes that what is the effective fatigue limit for a given number of over and underloads? Well, that we can answer by throwing some equations at it. So basically this problem can be solved with a system of closed form equations that is able to be numerically solved. So for each intersection point between the loading curve and the resistance curve, there must be this equality condition between them fulfilled, and there's in the resistance curve formula, there's this parameter AS that will shift the resistance curve based on the intersection point, the non-propagating crack length of the previous state. And if we add the effective fatigue limit, then we know that the loading curve must be a tangent of the final resistance curve. So there's additionally one tangency condition in addition. So demonstration of the model, here we are considering 3 loading spikes, and you can see the model working because the new resistance curve is always starting at the intersection point between the loading curve and the last resistance curve, and you can see that with the overloads the new resistance curve is modified, but not with the underloads. After 3 loading spikes, you can see an 18% reduction in the underload case, 7% reduction in the small overload case, and 40% reduction in the large overload case. So now we can plot the effective fatigue limit as a function of the number of loading spikes, and we see that the fatigue limit is eventually diminished in all cases. But the resistance curve shape affects the saturation of the fatigue limit. So for example, with the large overloads, because the resistance curve is predicted to saturate so slowly, the decline in the effective fatigue limit is very fast. But there's all the curves saturate to this limit value that is governed by the intrinsic threshold and the initial crack length. So this is basically just the load level below which the initial stress intensity factor is below the intrinsic threshold, and then there should be no crack propagation. But what this study does not consider is that the frequent overloads may still result in finite life. So this assumes rare overloads, and the damaging effect of the overload cycles themselves is not considered. So jumping into the conclusion, these recurrent loading spikes are very detrimental to fatigue limit and can even cause a decrease down to 1/3 of the constant amplitude fatigue limit with enough loading spikes. And both over and underloads can remove the existing closure and essentially reset the resistance curve. And these large overloads, basically the resistance curve shape can depend on the loading spike. So these large overloads may delay the saturation of the resistance curve and significantly promote the decline of the fatigue limit, which however saturates with enough loading spikes, and the limit value is governed by the intrinsic threshold and initial crack size. But keep in mind that this assumes only rare overload, so the damaging effect of the actual overload cycles will exist in addition to this demonstrated fatigue limit reducing mechanism. So ultimately it can result in finite life in the overload case. Okay, that was it. Thank you for your attention.
Thank you very much.